Welcome everyone to the EasyPower Thursday Technical Webinar Series. My name is Jim Chastain. I'm your host for today's session. And before I introduce our guest speaker on this popular topic, as we are in the habit of doing, we'd like to request some feedback from the audience. Again, no obligation or liability. And this is in the form of poll questions. And the first poll question is, are you aware of Class C and D Special Purpose GFCIs? And if you would respond accordingly. For all those that attend today, we will be supplying certificates of attendance. You'll receive via email, and you don't have to do anything else to receive it other than attend today. So it looks like we're about 3/4 of a way to the quorum. Let's give this another 5 seconds. All right. Here's how folks have weighed in. And so it looks like there's a lot of room for the information that's going to be presented. So you're in the right place. And then the second question is, how familiar are you with the Assured Equipment Grounding Conductor Program? And I, for one, am not that familiar, so I'm looking forward to the presentation in that regard. All right. Looks like we're about halfway to the quorum. Let's leave this open another 10 seconds. Thank you for participating. Here's how folks have weighed in on this one. So looks like we're in the same boat, and look forward to Mark's presentation. So without further ado, I'd like to hand the presentation baton over to Mark Pollock with Littlefuse.
Well, thanks. Is there anything else you wanted to cover before I get started?
No, the baton and the podium are all yours.
All right. Well, good morning, good afternoon, everyone. So thanks for taking a little bit of your time out of your week to join in on the webinar. And thanks also to EasyPower for having me here to present on the topic. I'm going to focus in and talk about shock protection. So nothing better to, than talking about electrical safety. Okay, so, my name is Mark Pollock. I'm responsible for the application engineering and our codes and standards efforts within the industrial business at Littlefuse. I am based in our engineering lab in Saskatoon in Western Canada. I've been with Littlefuse a little over 15 years now, working with protection relays, including ground fault relays, neutral grounding resistor monitors, arc flash detection, and other items as well. But today we will focus in on shock protection, like I mentioned. So I want to cover a little bit of some of these topics here to tell the story. I think it is useful to provide some of the background, just to properly frame it. So first, I'd like to talk a bit about the current state of electrical injuries, at least based on data from the US, and how we try to provide protection from electric shock, at that high level. Next, we can talk a bit about GFCIs and special purpose GFCIs, what these devices have been designed to do and how they provide that protection. And after that introduction, we can get in deeper on the ground monitoring interrupter function, or GMI, and how that function really acts in a proactive way to provide some additional safety. And finally, we can wrap up with a few changes relative to special purpose GFCIs that have been added in the 2023 National Electrical Code, which, if you're in the US, could soon be coming your way depending on your state adoption timeframe. So, getting into electric shock and some of the data. So this is a snapshot of the severe shock injuries and electrical fatalities that have occurred in the workplace over the last couple decades. And you may have seen similar graphs from other sources, but this particular data is drawn from the US Bureau of Labor Statistics, the census of fatal occupational injuries, which is really thought to be the most complete count of the workplace injuries. There, as you can see, there was a step change reduction in both injuries and fatalities when you compare this past decade to the one that preceded it. And so it's certainly very excellent to see that significant reduction of the injuries and especially the fatalities. However, the disheartening part is that we're still averaging 150 electrical fatalities, give or take, and almost 2,000 severe injuries every year. And that's an average over the past decade. Those dotted green and blue lines on the slide show that trend, and you can really see that they're essentially flat with not much for improvement or change in these last years. And the fatality number did drop down in 2020, which is good to see. But unfortunately, I guess I should make the note that the data here is the actual number of fatalities, not a rate, per hours worked. So that dip in 2020 is more likely due to the dramatic drop in some of the manufacturing activity when everything was stalled, during the COVID-19 pandemic. But that step change, just to kind of look back and look what was, had a very positive impact in the early 2000s, was often credited to OSHA's adoption of NFPA 70E and more focused and increased implementation of safe work practices. So the revised OSHA subpart that brought more awareness to those electrical safe work practices for both employers and employees was involving the use of certain equipment, training requirements, focusing on doing risk assessments, and expanded applications that required items like GFCI protection for portable equipment or temporary installations. NFPA 70E has, of course, gone through several more iterations since that 2009 version. The latest was released in 2021. And in Canada here, CSA Z462 is the equivalent document, and it contains much of the same content, but it is modified slightly to align with the Canadian standards and some of the Canadian electrical code requirements. The one thing I wanted to highlight is that in the 2018 edition, there was consideration added for human error, as that is a leading cause of the incidents. And that hierarchy of risk controls that's shown on the screen is really a good visual because it shows a way to evaluate the mitigation options to reduce the impact of human error on safety. So if we start with the bottom, where the tip of the pyramid, we're looking at the most basic items, which we would consider to be the last line of defense. So putting on that correct PPE, following procedures, with the administrative controls, those are important, but they are still subject to mistakes. So as we move up the pyramid to engineering controls, substitution, or even elimination, implementing those steps can fundamentally change the risk of the task and less subject to human error, and are as a result far more effective and desirable. So the NFPA 70E and the CSA Z462 documents are somewhat unique in the world of standards. So they have received a lot of attention and referrals, from a lot of places around the world. But for some that wonder about similar documents in other areas of the world, I did want to quickly highlight this. So this standard EN 5110 talks about the operation of electrical installations, but it does not get to that deeper level where it talks about arc flash hazards specifically or protective gear. But for anyone who is interested, there is a new project committee that has been formed, PC 128, that is set to begin work on an international standard for safe operation of electrical systems. So there will be more to come in this, in this arena around the world. Now we can take just first a second to talk about some of the risks before we get into further details about how to mitigate or reduce them. And really some of the common ways that people are harmed by electricity relate to shock, arc flash, and arc blast. So shock, the passage of electric current through the body, is obviously something that is a hazard. Currents as low as 50 milliamps can cause fibrillation. And one thing that is maybe not as well known, but we're only now beginning to see the research come out on long-term sequelae from low voltage shocks. And that's injury that can include psychological, neurologic or other physical symptoms that can become quite debilitating in later years. So that's maybe a topic of a presentation all on its own, but something that we're only finding out now about some of those things that can happen from the buildup of shocks in past years. Next, we have arc flash, which is that sudden explosion of intense heat and light energy that can really cause devastating damage and injury to any equipment or personnel that happen to be in the path. Of course, there's many calculations and codes and standards that have been developed and software tools to help take steps to protect against and understand and mitigate and reduce the arc flash energies, which is excellent. And last, we have arc blast. So this is the pressure wave that's created as the result of a thermal expansion during an arc flash. And in some cases, depending on the equipment, this can be just as dangerous as the arc flash itself. So, it could have also been a poll question, but we, could ask, so which of these do you think ends up involving hurting more people? And, when you look at the data, shock is responsible for the vast majority of injury events. And I don't want to degrade the other hazards because it remains critically important to protect against those. But if we want to have a meaningful impact on reducing the fatalities and injuries in the workplace, we really do need to have as well a focus on what we can do to reduce shock events. So on a previous slide, we talked about that hierarchy of risk controls. And if we think about that, already we have seen how one engineering control can have a very tremendously positive effect on electrical safety, and that is the ground fault circuit interrupter. So this data is taken from a report published from the Electrical Safety Foundation, and just shows a little bit of background about GFCIs. So the GFCI has been a hugely successful life safety device, and since the introduction in residential settings, in the US, there has been over an 80% drop in residential electrocutions and a 95% drop in consumer product electrocutions. Now, some of that is due to the product designs themselves, but it's undeniable that GFCIs have an impact here. So one of the things that's worthy of notice here is that this decline did not happen overnight. It took adoption of the GFCI into the National Electrical Code with expanded applications in all of the code cycles really since that first introduction in 1968. So GFCI protection was first required on some exterior outlets and pool circuits, then onto bathrooms, garages, basements, spas and hot tubs, and eventually kitchens in 1987. For the majority of its existence, that GFCI, whether we're talking receptacles, circuit breakers, or an inline cord device, really limited to 125 volt single phase circuits, 20 amps and below. But a more significant change occurred in 2017 that I want to highlight. So in that code cycle, NEC 210.8b, which is the section for GFCIs for other than dwelling units, raised the levels where GFCIs were required up to single phase 50 amps and three phase 100 amps. So at that time, there was increased usage of higher amperage equipment, and new GFCI devices were coming on the market that could offer protection up at that 100 amp level. So one example of an application that was affected, shown there, was the commercial kitchens. And the intent was to protect people using the deep fryers, dishwashers, and ranges that were reaching load currents up to that 100 amp level. And so you can see there really will continue to be changes to GFCI requirements as technology changes, because more and more of our equipment is now becoming electrically driven. So to quickly highlight, a little bit of the history, after some time working at GE and San Diego Gas and Electric, Dalziel, Charles Dalziel, went back to academia. And when he was there, a colleague had asked for his help to design a device to electrocute barn flies. And that research project really snowballed into a huge project because Dalziel realized the physiological effects that even small amounts of current can have on living creatures. So this took him from barn flies to livestock to human testing as well. And after a lot of research, experimentation, he gradually became a world authority, on this topic. So the realization that these shocks and fatalities were caused by ground faults, even on common circuits, led him to help participate in the creation of, the first GFCIs in the early 60s. So his research is what forms the basis of some of the IEC standards on shock protection. So this graph here showcases data from IEC 60479-1, which shows the effect that both the body current as well as the duration of that current flow will have on the severity of the shock. So we'll come back to this chart on future slides, but I just wanted to introduce that here. So when we purchase products, we often take it for granted that the product will do exactly what it claims it'll do in a variety of applications, even sometimes unexpected applications. So product standards are very critical for safety products to ensure that that the product is designed and can offer consistent performance and is actually tested to ensure it offers the stated protection. And UL 943 is the product standard that governs these Class A GFCIs. Now you can see at the bottom, there's matching Canadian and Mexican standards that are harmonized to allow manufacturers to build a product that works across the three markets. But this standard for Class A GFCIs is intended for products used on systems up to 150 volts line to ground with a trip level of 6 milliamps of ground fault current. And the trip time is based on an inverse time curve that's specified in the standard. Now there's many other requirements, and I probably put too many words on this slide, but suffice it to say that this standard requires the GFCIs to go through temperature and humidity cycles, undergo pretty severe physical and electrical testing, and make sure the device has functions like a self-check. So although products or other devices may claim they can trip at 6 milliamps, if it's not listed or approved to one of these standards shown here, you can't be sure it meets all those same requirements. So the main points to remember here for a Class A GFCI is a 150 volt line to ground device with a 6 milliamp trip. Now, just as a side note, technically the standard says it must trip at currents of 6 milliamps or higher and must not trip on currents 4 milliamps or lower, or even 3.5 milliamps and lower if the ambient air is less than 23 degrees Fahrenheit or more than 104 degrees Fahrenheit. So that is why you might hear people refer to GFCIs as a 3.5 milliamp or 4 milliamp or 5 milliamp device, but I'm going to use 6 milliamps for this presentation. So if we lay that trip level on that human risk curve, you can see that the 6 milliamp level of class A is below the level of muscular contractions. So in other words, it's below the let go threshold. And if the current is above the let go threshold, that means when the current is running through your body or your hand, it may cause the muscles to tense and you may not be able to physically let go. So when the UL 943 standard was designed, that value of 6 milliamps was selected on purpose, to be below that threshold. So the GFCIs that have been specified in the codes, which have done a great job of reducing those electrocutions, especially in the home, were all Class A GFCIs. And up until the 2020 version of the NEC, the definition of GFCI was a Class A device that tripped at 6 milliamps based on UL 943. And in Canada, there has been a definition that referred separately to a GFCI and to a Class A GFCI. But speaking in practical terms, the Class A GFCIs were really the only ones specified in the Canadian code as well. So these devices were mandated in homes and in commercial buildings and workplaces. But as we talked about, this is for devices 150 volts, line to ground and below. So it covers the handheld small tools and circuits, but it does not cover the high voltage circuits or the higher voltage circuits used in many production or industrial facilities. So UL recognized that demand, and we'll say opportunity, for GFCIs to also be able to protect at 480 volts and 600 volt, and with trip levels that could perhaps accommodate some of that industrial equipment that had slightly higher leakage levels. So about 10 years ago, the UL 943C document was released for special purpose GFCIs. So since, if you've ever downloaded the document, you can see it's labeled as an outline for investigation. And that's because it's a first release document that hasn't gone through the same UL standard release process, but product can still be listed to this document just as any other standard. So the UL 943C document is based off the same base requirements as the UL 943 GFCIs, but of course has a few very critical changes. So it outlines 3 new classes of special purpose GFCIs, which are Class C for circuits that are up to 300 volts line to ground. So in other words, a 480 volt line to line circuit. Class D for circuits that are above 300 volts line to ground. And so that would cover circuits like a 600 volt line to line. And Class E, that's also for circuits above the 300 volts line to line. The difference being Class D requires an oversized grounding conductor to make sure we're keeping a low touch voltage on the frame of equipment. So these special purpose GFCIs have a trip level of 20 milliamps. And as they're used on industrial equipment, this slightly higher trip level helps to ensure reliability. Now, in exchange for moving this trip level upwards, UL added another new requirement called a ground monitor interrupter. And this is a function that checks the continuity of the equipment grounding conductor to be sure there is a valid low resistance path before the load can be energized. So this document is really a game changer for industrial circuits because there is now a document that provides a path to standardized and listed devices for personnel protection that can be used on equipment at industrial voltage levels. So if there was a 480 volt circuit, this would be used with a Class C special purpose GFCI that would provide ground fault protection at 20 milliamps with integrated ground return path monitoring. So that's just to give you, to put those all together into one sentence. So putting this on that curve that we reviewed previously, you can see that the 20 milliamp is above that let go threshold, but it still does provide protection from fibrillation and is required to abide by an ultra-fast reaction time that is specified in the GFCI standard. Now, the focus of some of the future slides here to talk about the ground monitor interrupter feature also helps to eliminate a lot of the shock events from happening in the first place. So it's still a major step forward in providing personnel protection on these industrial voltages. So on this slide here, we're showing the inverse time curve that is used as the base for both UL 943 and UL 943C. That 20 milliamp pickup level, you can see designated with class C and D on the curve, is required to operate a little faster than the class A GFCI at that pickup level. So you can just trace the curve there to see the required reaction time at those current levels. Now, with this inverse time curve, it's designed to ensure the GFCI will trip faster as the current gets higher. And if you recall that previous human danger curve, that's because the longer the current is there, then the higher the risk factor can be. Now, there is a maximum point shown on there with the dotted white lines at 300 milliseconds for the special purpose GFCIs. And for any current that is above 300 milliamps, the device must trip within 20 milliseconds. The class A GFCI, in this case, would just be slightly slower with a maximum trip time defined by that formula you see on the page, and it works out, for those voltages where a class A GFCI applies to just be slightly slower. Now, we show on the screen there the EGFPD, and that's just a reference. Littelfuse also offers these equipment ground fault protection devices, and they are still built to these same standards and have the same protection curve, but they have adjustable pickup levels. And because of that, they're not considered GFCIs or special purpose GFCIs, but just wanted to mention them because they can help meet code requirements for heat tracing, de-icing, in marina circuits where those 30 to 100 milliamp sensitive pickup levels are required, but a GFCI may not be mandated. So while it may seem that the special purpose GFCI is not as safe due to that higher pickup level, we're talking 20 versus 6, it's not necessarily true. In a way, the special purpose GFCIs are a bit more proactive than the class A counterpart due to that additional ground monitor interrupter function. So just to quickly outline, the operation of the special purpose GFCI, the three-phase device, at 480 volt really operates on similar principles as a single-phase GFCI in your bathroom, except that it has a 20 milliamp pickup. So if a person makes contact with an energized part of that circuit, it allows current to flow through their body to ground, and the built-in current sensor can see that current returning to the power source outside of the power cables and react to it. A special purpose GFCI must also check the validity of the equipment grounding conductor. So it's shown on the slide here with that blue conductor at the top of the drawing, and sometimes that's referred to as the pilot wire or ground check wire. And the device uses that conductor to measure the resistance in a loop from the device out to the equipment through a termination device and then back to the special purpose GFCI on the ground wire. So this resistance is monitored to ensure that the equipment grounding conductor is intact and there's a valid low resistance path. If that grounding conductor goes open circuit, the unit will de-energize and remain tripped until that grounding connection can be reconnected. Now, the Zener diode termination, just to avoid confusion here, is not a requirement of the UL 943 standard, but that particular termination is something that Littelfuse uses to allow the device to detect if there is a pilot to ground short somewhere in the cable. So I want to focus a little more on the equipment ground conductor. And specifically, we can go through a few cases here just to compare the operation of a Class A and a Class C special purpose GFCI when they're considered side by side. So again, and I know I'm reiterating this point, but I want to make sure that it's clear that the purpose of that effective ground path is to provide a low impedance path for ground fault current to flow through. So the low impedance allows more current to flow and hopefully trip or even blow the upstream overcurrent protection very quickly when there's a fault. So in the image on the screen, you can see the brown, orange, and yellow conductors. That's your phase ABC, while the green conductor would be your effective ground path, providing that path for ground fault current to flow back to the upstream source. So if the effective ground path becomes compromised, just like we're showing under that magnifying glass, the fault current may not be able to return to its source. And when you say that there is no fault current, that means the GFCI will not trip. Now, in that case, the frame of the equipment can become energized, just waiting for someone to touch it and for their body to perhaps provide that alternative path through their body to another grounded surface or piece of equipment. So when somebody completes that circuit, their body's higher impedance causes much lower levels of fault current than would normally flow if the fault current was going through that effective ground path. That's, that current could be so low through the body that a regular overcurrent device like a fuse or circuit breaker is not able to sense the fault. And that really is why the GFCI was brought in, to be able to interrupt the circuit really quickly, even with low levels of current that are flowing. Now, unfortunately, for a GFCI to perform that job, ground fault current must be already flowing, which could mean somebody is getting a shock. So if we pose this another way, what if we could identify that shock hazard, like an energized frame, before a person was actually shocked? And that is exactly what a special purpose GFCI can do. So I want to show a simplified circuit and then get into a few cases here. This is a normal three-phase load connected to a Class A GFCI. As you can see, the green conductors shown on the drawing are the equipment ground conductors between the load and the GFCI, and from the GFCI upstream to the grounded power source. Now, if we add a ground fault from one phase to the equipment frame, the fault current will flow through the grounding conductor back to the source. So this path is the intended path with a low resistance, which will help minimize the voltage that could be present on the frame. And the current sensor can immediately detect this fault current, and the GFCI will trip within the time specified by the UL 943 standard. Now, if we take the same case with the ground fault, but now we add a broken ground conductor that has occurred at the same time, and this will interrupt the ground return path. And because that path is interrupted, there is no path for that fault current to flow back to the power source. That means the GFCI will not be able to trip. So the net result is the frame becomes energized at line to neutral, potentially giving someone a shock if they come into contact with it. So when somebody does make contact and the fault current is flowing through them, the GFCI will be able to measure that and trip, again, as specified by the standard, So the GFCI will stop the shock very, very quickly and probably save this person's life, but the shock does begin to occur before the GFCI can take that action. Now, when we think about industrial equipment, just want to highlight one thing here. So you can see that photo with the piece of equipment used in food and beverage. The yellow flexible cable is coiled up there. So that cable is the link between the equipment and the power system. And with cable laying around, it's easy to think how cables can be cut, run over, pinched, stretched, which can cause damage to the grounding conductor. So that's really one of the reasons why people receive those shocks on the 480 or 600 volt equipment. When a ground fault occurs, the breaker may not be able to sense the current because of damage to that grounding conductor. So let's take a look at a few very specific cases and compare a Class A GFCI and a Class C special purpose GFCI. So both devices, as we mentioned, rely on that UL 943 trip curve. There is that small difference I mentioned in the operating speed when we get to the very high current levels. And that's just because the special purpose GFCI has that requirement to cap the reaction time to 20 milliseconds for those high currents above 300 milliamps, while the Class A GFCI has a formula to determine that based on voltage. So we'll go through 4 cases, one with a ground fault with an open grounding conductor, another with ground fault with an open ground with a human contact, ground fault with intact or healthy grounding conductor, again with human contact, and then what if the ground fault and the open ground happen at the same time along with that human contact? So in this first case, you can see we have a ground fault present in the motor on the saw, and in that red circle, you can also see that the grounding conductor has been severed. So with the Class A GFCI, as we've discussed, the saw, when the saw is energized, or we'll say when power is applied to the saw, it could run and appear to be working fine. But that ground fault has energized the frame of the equipment to line to ground voltage, and the GFCI is not able to see that or trip because there's no ground fault current flowing due to that broken ground. Now, by comparison, the Class C special purpose GFCI would not allow this saw to be energized in the first place due to the broken grounding conductor. So that is something where the shock risk is just not even allowed to be present because that ground monitoring has taken the proactive stance of detecting that loss of ground. In our second case, let's add a human contact here. So in the red circle, again, you can see the severed ground. And this time, the ground fault is created by contact from the yellow to green conductors. Now, when you have cable damage like that, it's not too difficult to believe that that could have occurred. The Class A GFCI could allow this machine to be energized and possibly run because there would be no ground fault path for the ground fault current. Then when the individual comes into contact with that equipment, there is now a path for fault current to flow through the wet floor, through the person, to the frame of another piece of equipment behind them, and then back through the ground conductor on that second piece of equipment to the grounding system. So the Class A GFCI would sense that fault current once that connection is made and trip within that UL 943 mandated trip time. Now what we've shown here, if we use, we'll say a 500 ohm body impedance model for wet contact, this shock could be about 240 milliamps, which when you do the math would be tripped by the GFCI in 29 milliseconds. For dry contact with a 2000 ohm body impedance, the shock could be about 60 milliamps, which would be interrupted within 208 milliseconds. And perhaps for a more indirect contact, looking at about 20,000 ohms as that body impedance model, the shock would be way down to about 6 milliamps and would be interrupted by the Class A GFCI in 5.6 seconds or less, which is the time off that inverse time curve. Now, on the Class C special purpose GFCI side, again, in this case, the equipment would not even have been allowed to be energized, as the ground monitor interrupter circuit would detect the severed ground and not allow the equipment to be started. So again, the proactive nature of that ground monitor would have removed the possibility from someone even touching the equipment to receive a shock. So looking at case number 3, we're considering the case of a normal, healthy ground conductor in the cable and a ground fault in the equipment. And now, again, the same cases of a human making contact with that equipment. Now here, both the Class A GFCI and the Class C special purpose GFCI would initially allow this equipment to be started. And based on the calculations with the cable type that we had shown on that slide earlier, the fault current could be up to about 1,000 amps, returning through the equipment grounding conductor. Now, this is, how the low resistance path of that grounding conductor is important, because the person touching the equipment is in parallel to that equipment grounding conductor. So the shock current that they will receive will be based on the ratio of their body resistance to that equipment grounding conductor. So in these cases, the devices are seeing the same current, but as we talked about before, because of the different maximum trip points, there is a small difference in the reaction time. So the Class A GFCI would respond in approximately 29 milliseconds. So that's based on that maximum trip value in the standard of the time equal to 10 over the voltage to the power of 1.43. The Class C special purpose GFCI will respond slightly faster at 20 milliseconds, because that is the maximum value specified for all faults above 300 milliamps. Now looking at the final case, considering the ground fault and the damaged or open grounding conductor all happening at the same time, along with human contact on the piece of equipment. So we can see that the Class A GFCI and the Class C special purpose GFCI will react in similar timeframes for both the 500 ohm and the 2000 ohm body impedance model calculations. And that's because both devices are based on that same inverse time curve from UL 943. However, at that 20,000 ohm level, there is a difference. So at the 20K value, that fault will create about a 6 milliamp current that would be going through the person, which would cause a mild shock. Now this is detected by the Class A GFCI and will trip in less than 5.6 seconds. Now, in the case of the special purpose GFCI, the Class C, it has a trip level of 20 milliamps, so it would not respond to the 6 milliamp fault current. However, that ground monitor interrupter feature that we've been talking about would be detecting that severed ground, and that will cause the device to trip. Now, there are devices on the market that can de-energize the circuit based on the response from the ground monitoring in under 500 milliseconds. And certainly, due to the safety benefits of a fast-acting GMI circuit, we really would recommend a device with that trip level under 1 second. So we can see here is where it comes into play. And even though that 6 milliamp current is below the pickup level, the device is still engaging and responding and reacting and turning off the power quite quickly. So the net result is still to remove the hazard faster than what the Class A GFCI would in that case. Now that we have really gone through and hashed some of the ground monitoring functionality, just want to show one other aspect of the application. So I mentioned before that the pilot or the ground check conductor is typically used to perform this ground monitoring. So on the photo here, just showing one example of a cable on the left that has that additional pilot wire included. And couplers are also available that have the pilot pins included in them. Some couplers may have one pilot, some may have two. So these type of couplers and cables incorporating that additional pilot wire and that pilot pin have been used in a lot of different heavy industries for decades, but it is a little bit of a new concept for some of the light industrial facilities. Now, a separate wire, when I'm talking about a wire, I'm talking about that pilot wire, could be run to provide that ground monitoring loop. But as you can imagine, it really is much easier and much safer to have that integrated. And again, to recap on that point, this ground monitoring circuit is a mandatory part that was added to the Class C, D, and E special purpose GFCIs. And it's something that in the Class A GFCI standard, there is no requirement for it. So it certainly is not a required function. But there's also nothing stopping from manufacturers from offering that in a Class A device if they so chose. So I've, I think, reiterated this point many times, but just one final way to talk about it here with the ground monitor interrupter circuit. When you look at the safety of, let's say, receptacles or drop cords that are perhaps sitting in a facility and not being used or disconnected, the equipment grounding conductor is open. And so that means that if this was a 480 volt or 600 volt receptacle or cable and was protected by a special purpose GFCI, it would be in the trip state because the grounding conductor would be open circuit. That means that the receptacle on the wall would have no power. So that also means that there would be no shock hazard that can be caused by accidental contact or something else, water in the plug. And that goes a big way to reduce, some of those shock events. So only after the plug is connected and that ground path is verified all the way to the load equipment, that's when the special purpose GFCI would allow the circuit to be closed and allow the equipment to be energized. So now that we've really covered what special purpose GFCI is all about and how it's different than some of the traditional GFCI protection, we probably can take just a quick look at a couple code changes that have already happened that incorporate this technology. So in the 2023 edition of the NEC, one of the major changes that anyone will first see if you've looked at it is all the definitions being centralized in Article 100. So in Article 100, there was a new definition added for a special purpose ground fault circuit interrupter. And as shown, it states that it's intended for applications where voltage to ground is above 150 volts. And it does mention the Class C, D, and E devices according to the UL 943C document. So while it doesn't say it in the words there in the gray box, as we've talked about, these devices, they do follow the same trip curve as the Class A device, but they do have that 20 milliamp pickup level. One application that was modified in the 2023 NEC codebook is for horticultural lighting, and that's in Article 410. So as the demand for these facilities has continued to grow, and yes, that is pun intended, there are larger and more lighting systems being installed. And these greenhouse applications, you know, they can be a challenging environment because it is very wet. They may have automated irrigation systems to keep plants constantly watered and very high humidity. The lighting systems, you know, use flexible cords and separable plugs, and that provides flexibility in the setup and to be able to expand or modify or move them around as the facility changes and depending on what they might be growing. Now, just for a little bit of history there, the requirement for that Class A GFCI protection was first added in NEC 2020. And as we've talked about, this applied to lighting systems that were then 150 volts line to ground and below. The code did mention all systems employing a flexible cord, but that was actually a wider requirement than the code panel had really intended. So in 2023, they corrected that language to say that lighting systems with flexible cords and separable connectors and plugs is where the GFCI requirement comes into play. You know, that was the intended target all along. Now, since 2023 NEC was also adding special purpose GFCIs, the code making panel also took the opportunity to add that requirement to have lighting circuits above 150 volts to ground use the special purpose GFCIs as well. And second, Article 680 in the NEC is where there's other changes relative to special purpose GFCIs. So this article deals with, you know, all the electrical wiring and equipment for swimming pools, fountains, hot tubs, spas, both, you know, permanently installed or storable. And it also applies to metallic auxiliary equipment, you know, the pumps, the filters, and the like. So it is quite obvious that these are wet areas which have a high risk of fatal shock if there's any equipment degradation, any malfunction, any improper water ingress, or other damage. So in 2023, the code was updated to essentially say that in all areas where these GFCIs have been required, where Class A GFCIs have been required in the past, if in those applications there is equipment or service installed above 150 volts to ground up to a maximum of 480 volts phase to phase, that it now must incorporate a special purpose GFCI. And this does cover both receptacles, which would be the terminology for plug and cord connections, as well as outlets, which would be a hardwire connection. Some of the specific clauses, you know, are shown here on the screen, but this includes receptacles near permanently installed pools, both indoor and outdoor, electrical equipment used with the storable and portable spas and pools, outlets supplying self-contained spas, receptacles near fountains, and outlets supplying non-submersible pumps. So at the end of the day, the summary is, wherever those Class A GFCIs were used, in general, if there's equipment that now goes above that 150 volts line to ground, up to a maximum of 480, then a Class C special purpose GFCI would need to be used on that higher voltage equipment. So as we come to a close, I wanted to make one quick plug for the IEEE Electrical Safety Workshop. if you're involved in the world of electrical safety, this is a fantastic event to talk with not only manufacturers, but a lot of end users, a lot of consultants, a lot of everybody trying to understand how to design a safer workplace. And so this conference is an excellent place to do that, and good thing to put in your calendar for March of next year. So with that, that finishes all the slides. I know I ran pretty close to the end of time, but if there is a question or two we can try to answer quickly, we can do that.
Mark, most of the questions came in, I think you covered many of them with subsequent slides, but you may look at your chat box to see if any are short answers.
All right, I'll see if I can quickly look here.
And again, if we can't get to them, we'll send out a Q&A list via email afterwards.
Okay. Well, I see one relative to the ground monitor circuit, distinguishing between a good equipment ground and a secondary ground. And what I will say is the ground monitor circuit is designed to make sure there is a low resistance path from the frame of the device that's being powered, back to the power system. So if there are parallel electrical paths that exist through other things other than the equipment grounding conductor, it is potentially possible that those could be part of the measurement. It may not be possible to have that as fully isolated, we could say, but the fact remains that it is still verifying there is a low resistance path, which will still have the net effect of providing that protection to ensure there is a low touch voltage on the frame.
Mark, thank you for an excellent job. We're out of time now.
Okay.
But we will circulate a Q&A list to everybody that attended, and we look forward to seeing you at the Electrical Safety Workshop next year.
Yes.
Have a good day.
Thanks, everyone.